when we try and generalize derivatives to two variables, we can have either the change in z divided by the change in x, right? So we can measure the slope as you travel east-west.
The change in z.
Oh, sorry, yep. Sorry, yeah, so whenever I say z, assume I'm talking about my function output. We can talk about the change in height as you travel east-west, or we can talk about the change in height as you travel north-south. Right, so these sort of measure two distinct notions of rate of change. Right? This is as you travel in the positive x direction. This is as you travel in the positive y direction. So each of these is sort of partial information about the rate of change of our function. So we call these the partial derivatives. And we write them in this fancy way, like this. Okay, so this is a fancy style D to distinguish it from the usual differentiation. So we'll call this dfxy dx. Okay. These are not 2's. They look a lot like 2's, but they are not. Okay. And this is dfxy dy. Okay, so the change based on y. Yes?
So is this the derivative of a contour plot?
Yes. This is the derivative of a contour plot. And we'll show how that interpretation looks in a moment. Yeah.
That's different from the derivative of
Yes, that's a different thing. So these are the slopes of surfaces. Right? We've got some surface living in space. Right? We've got the plot of f of x, y. And this is how that plot is changing as we move. Okay. Another notation for this, because this is a lot of symbols, is to write a sub x there. So f sub x.